We can check and make sure that we're live before we get started here. I'm tired as well. So, do I want to be tired during this? No. So, let's pull this up. Started streaming a minute ago. Trying to pull it up on my phone, but I can't right now. I mean, I'm seeing it right here. That's fine. If I go to videos. Newest. Here it is. Got it. We're good. Videos. Alright. I got this, got the YouTube chat on my phone, and then we can pull up Twitch as well. So we'll be good on this. Dope. English IRL creative, and then we could just add a couple more of these. I don't know why it removes them. It's pretty dumb. I gotta get my shit together, dude. I am very not together. I don't even know what I'm doing, dude. You know? What am I? Am I in the entertainment industry? Or am I in the software technology industry? It seems like I'm being forced into entertainment. And I kind of hate it. I hate the entertainment industry. It's terrible right now. It's almost like numbers game. Finance based on popularity. Weird world, you know. If I would have known that in high school, I'd be a freaking, not a billionaire, but probably a millionaire. So what are we doing? What exactly are we doing? Session restored. We don't need any of this, right? What do we got? We have some data here. And then we have this stuff, right? Did I download all these data files? Let's say that this is irrelevant, right? Okay, here we go. More relevant, right? Here we go. Read frame. If I could start streaming again, that would be nice. Just so lazy. I don't know what it is, but I just am so freaking lazy. So we should be able to see this stuff, I guess. It's the thing. 1, 2. We don't need to open it. No. Why doesn't this one download? I need to save this file, apparently. Whatever. Yeah. I don't care. So we've got some waveforms. Now, what are we doing? Download the Python functions to read the data. We have this. wget, for example, put these files in your current directory. Sounds good. We're using this, so let's just bloop, you know. Some HD5 files, and then we put the waveform file in there as well. Now, if we open this, let's see what we got. Process.py. So we have matplotlib. Can we run process.py? Let's try that. Deprecated. Use data set instead. Use data set instead. Okay. It's not even in here. I don't see it. Dataset.py. Where is that? What's up? What's up, Mose? How's it going, dude? How's it going? We're doing some coding. You know, it's probably not that fun. I don't even know why I'm live streaming it. I'm literally just live streaming it for reference, in case I want to look back on any of this stuff. It's more just me learning, so it's probably not very interesting for anyone to see. But I do want to record it. I guess I could record it, but live streaming doesn't save it to my computer, so it saves data on my computer. So let's see. So what are we even running here? How about we start from the basics? Let's do this. We don't need all this junk. Process.py is what we're dealing with? Or what? Seems like it, right? Because it gets down to this. Yeah, so it is. Okay. Let's start with that. Python process.py. We have some freaking crud that we don't need. What does this say? Python is installed as a framework. Python version. Okay, what is this? Nick, I am a prep for full-time interviews this month and next. Ben Grind and Leak Code. Oh my god, I forgot the freaking screen on OBS goes black if you go full screen. I have to figure that out. Full-time interviews this month and next. Been grinding on Leak Code. Still having trouble with easy and medium. Any suggestion? Well, you're gonna have to get good at easy, dude. I mean, I made a video on it. I made a video how I passed my Google and Uber or whatever. I'm actually making a course, dude. So I mean, if you check out the course, I mean, it's not fully done, so it sucks that I do have some stuff that I don't put on YouTube on here though. And I'm making it over time, but I would say you're definitely gonna want to freaking be good at easy ones. I mean, we're starting to get into some good stuff though. It just sucks because you could do one a day or two a day of these videos, but it's tough to develop an entire course really quickly. But I got like, I think I'm almost done with week 1 out of a 10-week course. So, hopefully you pass by then. But if you don't, that might be a good resource. Besides that, though, I mean, I made a video on it, so I guess all I would say is just you have to just do them every day, like all day. That's like literally the main thing. I really want to do every single problem and put it on the internet so people could have solutions, but it freaking sucks, dude. Dude. All right. Dude. I want something else to get me through this. Da-na-na, man-na-na. Da-na-na, banana-na. And I want something else. I'm not something when you say goodbye. Alright. So what does this say? Note, in general, LIGO strain data time series has data gaps filled with NANDs. When the detectors take invalid science quality data, analyzing these data requires the user to loop over segments, valid stretches. We provide example code to do this. Okay. Segments is this. You go through, you loop through. I feel like we already did this before. Timeline, Fourier transform. In 4096 seconds of release data around GW150914 is an unbroken segment with no gaps, so for now we'll read it. Treat it as one valid segment, ignoring the extra complexity mentioned above. For LOSC data releases, okay, we don't care about any of this. Show me the money. Show me the money. Copy and paste. And then it breaks. Broken. Use data set instead. Okay. I just don't see what they mean by that. Load data. Okay, big deal. I didn't even do anything. Dataset.py. Dataset.values has been deprecated. I just don't really know what that means. Okay, makes sense. If I can't solve a question within 30 minutes, should I just look at the solution? What's the process when you can't solve it? Oh, dude, yeah. 30 minutes is probably perfect time. I would say, dude, if you can't solve it in 10 minutes, look at it, bro. If you can't solve it, you can't solve it. Don't act like you can solve it if you just stare at it. I mean, you're going to waste all your time if you sit there and stare at it for an hour. When I was doing it, I was like, I'd look at it for a few minutes and I would be like, okay. You read it and you're like, I know how to do it or I don't, It's not something, I know there's ones where you partially know how to do it. Those maybe spend some time working through, but if you have no clue, I mean, what are you even dealing with, dude? You got to start if you have no clue, look at the solution, look up some YouTube videos, figure it out, and then look up problems similar to it, figure those out, then do different problems, go back to those problems. Adding numerical relativity templates. Yeah. Okay. Now let's also read in a theoretical numerical relativity template generated. Okay, that doesn't help. We have nothing going on here that is helping us. So lame, you know. Dot value. I don't have any dot values. That's the problem with my code right here. Read LIGO.py. We must be using read LIGO.py. That's got to be it. You know, read LIGO. Here it is. Yeah, I see the problem now. I see the problem. Problemo. Okay. I see. So, thanks, Nick. Gonna sign up for your Patreon. I could tell you have a good heart and want to help. Thank you very much, dude. Yeah, I mean, I do. I really want to do all the problems, and I really appreciate that if you do sign up for that. That, you know, those, I appreciate it because what I'm doing is I hired one of my friends and I pay him $10 an hour, and I don't have the money to, I don't have the money to have an employee right now. But I've been paying him to just come and film and edit these algorithm videos for me the whole summer. So I'm like negative. I mean, it's not like I'm in debt or anything. I have a job and whatever, but I had to spend thousands of dollars on this stuff. So when I get support, it is very helpful. And the people that hit me up on Patreon, you ask me a question and I will get back to you. Really, if you ask me a question in general, I'll get back to you. If you go in Discord or whatever, but Discord is fine as well. But yeah, people that I would say if you're gonna comment or something like that, I do not get back to comments. I like the comments, but there's a lot of my thing is growing actually a lot. You probably can't tell from nobody watches these live streams, but we're in the thousands now, which is good. And what is I saying? There's a lot of comments. I get like 2,000 things a day, so I cannot respond to comments or Instagram messages. I don't, but Discord and Patreon, I check every day, once a day. I respond to those messages in Discord and Patreon. So either of those, hit me up. But also do not send me, I would say what I do is I don't, I've had people that just send me problems that they're having. I mean, imagine I'm just solving people's problems all day. That would be pretty, I'm good with it, a little advice, but, I've had people like, hey, this is my code, I have a syntax error here. What the heck is the problem? I'm like, dude, you're missing the letter S. And they're like, oh, thanks. And then you do that 100 times. It's like, all right. But, I'm sure that, you probably wouldn't do that. But I have had people do that. And I have had people get mad that I don't answer to, like, Instagram messages. And it's like, dude, I don't just sit on Instagram, looking at messages and stuff. It's interesting. Okay. What are we doing here? We have this data. We're obviously having these errors. What are we seeing? Dataset.value has been deprecated. Use this. Use the braces. So that is the issue here. So what that means is we want to get things using the indices brackets, maybe hash maps, etc. So we have SD strain SD dot value. So we can't use value. So what we'll have to do, what we're going to have to do, dude. We are going to have to add some print statements and actually go through this and figure it out. I mean, they've got some outdated shiz here, which stinks. But it is a sample thing. We're going to have to go through, figure it out. Strain or SD, we could print SD, figure that out, and then we could easily replace this if we just figure it out once. So it shouldn't be that difficult. Actually, we want to do, actually this is fine. Boom. So here's what we have. We printed, what are we printing? Dataset value. Python read ligo.py, and it ran. That's interesting. But this one doesn't run. Now why is that? Try. Oh, we're looking at a specific method, read frame. So what gets called first? Okay, what are we doing here that is calling this, right? Because it looks like we can run this file, right? If we do Python read ligo.py, runs pretty fine there. That's, you know, something to consider here. Burp. And also, you know, with that being fine, you know, that's fine and all. But what are we using out of this? We have as RL. So we're calling load data. There's the issue. So in load data, you know, we're figuring this out as we go here, guys. Read ligo.py. Load data. Here's the method we're dealing with. And now where's dot value within load data, you know? This is apparently the problem here. I'm assuming. Right, load data, RL. Yeah, all we used is rl.load data. So if we look at this method, is it calling another method though? os.stat, arrange zeros. And we could actually look this up. So 313. Excuse me, sir. What? How is it 313? 313 is literally a comment, bro. Maybe if we vim. No. File list. You know what it is? It's probably right here. Okay. So if we just remove these, you think that's the issue? So DQ info. Let's print DQ info. So here it is. Here's DQ info. We're actually getting somewhere. HD5. It's just debugging, which sucks, but it's fine. HD5 group quality simple. I don't really know what that means. So let's get more specific here. Let's do this. shape, short names, dot value. What does that mean? Use data set instead. Like this? No. That's wrong. Dataset is not callable. Okay. I just don't know what value, what they're talking about, I guess. There's nothing in it. Huh. This is weird. Shape and type. I mean, I don't know. So wait. Oh, this is where we have. This? Is this really what I have to do every time? This is how you get value? Is this person on crack? What? What is this? That can't be right. That is right. Wow. It's interesting. Okay. I mean, whatever. It's freaking whatever, dude. Dude. Figuring it out. We're figuring it out. Alright. Hopefully we didn't break anything. So, Matrix Man, let's go. How's it going, dude? What's up? Let's pull this out just in case anyone does talk on this. Dude's coming over from Twitch, or how do you know my Twitch name, dude? Are you from Twitch, or are you, just familiar? Let's see. So, we have figured this out officially. Now we can continue going here. LOL, I just remember it. Yeah. I'm making a comeback, dude, I don't know, dude. I don't know. I want to be... I don't want to be where I'm at right now, I'll tell you that. I thought I was going to be much farther ahead. But, the YouTube is growing. If I just eat... I don't know, bro. We'll figure it out. We will... Maybe if we move to Boston and we start going to Harvard and MIT and stuff like that, we build out this course, and I build out this platform, and I solve some pretty intense problems, and we start a company or something, pretty cool company, that might be the move. I just don't know what I want to do, dude. I have a job, I make YouTubes that kind of suck, and I am bored, so I'm trying to figure this out. We will be elevating at some point soon. It's only been a couple months of this lifestyle, but we do need to switch it up, dude. We're gonna get moving soon. This is a good start to it. Doing black hole research can only lead to positive things, right? How could doing black hole research be negative? So let's add theoretical numerical relativity template generated with parameters favored by the output of gravitational wave parameter estimation. Okay. Should we read this paper? How important is this paper? You know? Is this like the most important paper ever? On September 14th, two detectors, laser interferometer, gravitational wave observatory, simultaneously observed a transient gravitational wave signal. Signal sweeps upward with frequency 35 to 250 hertz, with peak gravitational wave strain of 1 times 10 to the negative 21st. Okay. Relativity and spiral merger, pair of black holes, and the ring down of the resulting single black hole. The signal was observed with a matched file, signal to noise ratio of 24. Okay. Cool. Not really a paper, is it? I mean, what is this the paper? Who wrote this? You know? This is LIGO. This is the LIGO paper. It's legit, dude. This is pretty legit. It's only a few pages. We can scan through it. Introduction, 1916, after the final formula field. Okay, whatever. Einstein predicted general relativity. We detected corresponding the predictions from general relativity are in alignment with what we detected, right? That's the gist of it, I'm pretty sure. This numerical relativity template corresponds to the signal expected of a pair of black hole masses with 36 to 29 solar masses merging into a single black hole, 62 solar masses at a distance of 410 mpc. Condense the template time series with the following URL. Put it into your directory. Okay, we already have that, don't we? Pretty sure we already have that, so it's fine. But we will add that line into this, you know? Did nothing. Oh, crud. We got some real crap going on now. Look at all these print statements, dude. So what are these? And then we have an error? None type has no length. Strain L1. None type has no length. Okay. Strain L1. Let's print strain L1. Strain L1 is none. Why? Oh, I hate this. Why though? You know? Do we have this file? -32. Oh, we have duplicates. 2016. We don't even have the files we need to V1 1126 1126 259 446 32 HD5. Okay. That looks right. So I don't know what the deal is with that. This also looks the same, though. Is this right? What the hell? 32? Yeah, that's fine. Oh, LL1. LL1, here it is. See, that's the issue right here. What we're seeing is this freaking 1. Boom. See that? We don't need these 1s here. And now if we print, there it is. Just like we wanted. So yeah, that's good. Adding numerical relativity templates. We already did all that. It doesn't really matter. Here we go. Here we go, mate. Now we're getting into some plots. The main, part of this, the thing that matters, the plotting, correct? Where's the plot? Just closed, though. Save fig. .png. What is that? What, dude? How about no? How about this, dude? What? Where's this plot going? What about this? There it is. What are we seeing here? We're seeing something. We got some data going here. It's interesting. GW150914. Now, what do we do with this data, and what does it mean? That's a major question. We need some answers. That'd be savage. Don't do. Could you imagine? Alright. Looks like we got some stuff going on. So, that's great. I don't really care that much. We probably have to mess around with this stuff a little bit, though. So here's the time of the event. Seconds around the event, 5. Okay, let's increase that. Let's look at 10, dude. Can we quit this Python plot? I don't need it. So here's 10 seconds. Let's go like 30. How long is the event? This is a freaking merger, dude. Let's do 5,000, bro. It's a long time. I don't think the event goes that long. Okay. Time in seconds. So I put 5,000 and it did essentially nothing. Negative 15, bro. I mean, we're not even... Does this do anything? No. Okay. What does this do? Nothing. Nothing. That does nothing. Nothing. Oh, and nothing. Okay. So what we're seeing here is that this does nothing. Delta T. T event minus delta T. Time H1 less than T event plus delta T. Okay. Do we need to read an entire physics book to even know what's going on right now, guys? I don't think so. I think we'll figure it out. Index for the strain, time series for this interval. Okay. LOL. How about this, bro? How about we just do this? Let's see what happens if you do this. Now we're talking. Oh, yeah. Cool. This is a Boolean. So, we don't even need this. True and true. How about that? Ha! There's a better... There's something a little bit better here. Let's go to 50. What happens at 50? Nothing. Okay. So we're getting nowhere now. Six? Trash. Okay. So we don't know what's going on still. We're at 5. We don't need true and true anymore. Okay. Of true. Okay, this is fine. This looks fine to me. What else do we have? Bits, chin, whatever. Who cares? Alright, we plotted. Whatever, dude. We get it. The data are dominated by low frequency noise. There's no way to see a signal here without some signal processing. There are low frequency oscillations that are putting the mean of L1 strain at negative 2.0 E minus 18. Some of the problems, what does this say? Some of the problems you just have to do it so many times, it becomes second nature. Yeah, dude. Facts, I would say. I mean, that dude left a while ago, though, so a little late for the advice. I mean, I don't know. Maybe he's still here. I don't know. Alright. What are we doing? So, low frequency noise. We want to find the signal. What's up? What's up? Emin, Emine, 0905. How you doing? So there's low frequency oscillations that are putting the mean of the L1 strain at -2. This is L1 green at the time of this event, so it appears offset from the H1 strain. These low frequency oscillations are essentially ignored in LIGO data analysis. See band passing below. We will be whitening the data, whatever that means. Data in Fourier domains. Fourier transforms are very important in this, apparently. I'm not an expert. I watched some YouTube videos on them. Maybe we need to be experts, maybe we don't. But we will become experts if we need to. So we're good. Plotting the data in the Fourier domain gives us an idea of the frequency content of the data. A way to visualize the frequency content of the data is to plot the amplitude spectral density. Amplitude spectral density, or the square root of the power spectral densities, which are averages of the square of the fast Fourier transforms of the data. Okay. They are an estimate of strain equivalent noise of the detectors versus frequency, which limit the ability of the detectors to identify gravitational wave signals. They are in units of strain RT hertz. So if you want to know the root mean square strain noise in a frequency band, integrate sum the squares of the ASD over that band, then take the square root. What? Okay, cool. Whatever that meant. We have to pay attention, apparently. If we want to understand that, we're going to have to pay attention, dude. And I was just reading it. I hate this. This is hard, dude. No wonder people get freaking awards and crap for being smart. You know, this is like actually pretty hard. So we're going to have to read it one more time. ASD, amplitude spectral density. What is it? It's like the sum of squares or something like that. ASD is the square root of the power spectral. So there's power spectral densities. Amplitude spectral densities are the square root of those. And the power spectral densities are the average of the square of the fast Fourier transform. So the average of the square of the fast Fourier transform. Okay, how do we find that? So we have to do a fast Fourier transform and then square it, I guess. We take the average of the squares. Okay. They're an estimate of the strain equivalent noise of the detectors versus frequency, which limit the ability of the detectors to identify gravitational wave signal. Strain equivalent noise detectors versus frequency, which limit the ability. Okay, sure. They're in units of hertz. Did I put deodorant on? I don't know. So if you want to know the root mean square in a frequency band, integrate the squares in the ASD over that band and then take the square root. There's a signal in these data. It's not even a sentence. For at the moment, let's ignore that and assume it's all noise. Okay? So we'll add all this stuff, dude. I get it. I see what you're saying, bro. I'm on your side here. Let's run it. You know what? We don't even need this chart going. Let's comment the chart out for a minute. Bravo, man. Oh, we have this. This is the picture of it. Wow, you could just save it as a picture. It's pretty neat. Hey, Nick, when you get a chance, share the link to SoundCloud. It's not working right now. SoundCloud? What's up? Wait, what are you trying to check out my SoundCloud for, dude? I think I took everything off SoundCloud, but I could set. Yeah, I'll show you. I'll send you the link. .com. Let's check it out. think it's this. No. I don't know what it is. Nick White. Oh god, that's not me. No. Nick White. Nick W. Okay. Boom, there it is. It's right here if you want to check it out. Looks like I got some songs up here. I don't think I have any of mine though. But yeah, no, those are just beats. So yeah, it's not that fun to check out, but it's all on my YouTube, all that stuff. So it doesn't matter. So there we go. Let's check this out. What did we do again? Matplotlib deprecation warning. I don't care really about warnings. You know, what I want to do is show the freaking plot, though. I'm down with that. Okay, so we got two different plots now. And these are more, I guess, the gravitational wave signals. You know? From what, I guess from what we just read, right? Obviously. It says this is crap. Then we do some processing, and we get this. Now, what does this mean? Who frickin' knows? But, you know, we're getting somewhere. We're plotting stuff, I guess. That's good. Not really, but we're doing stuff, so it's all good, dude. Just kidding, but we're getting down to, you know, down to business here, it looks like. You know? So, note that we only plot the data between fmin 10 hertz and max 2000 hertz. So between 10 and 2000 hertz. Okay. Below fmin, the data are not properly calibrated. Okay. That's okay because the noise is so high below fmin that LIGO cannot sense gravitational wave strain data from astrophysical sources in that band. Okay, that makes sense. I was told that by a mentor before that we processed the data between 10 and 2000 hertz. I remember being told that. So that rings a bell. It's just, you know, the boundaries that LIGO can actually understand the data and detect it, and we can do stuff with it. Okay. So the sample rate is 4096. Okay. I don't know what that means. 2 to the 12. Still don't know. So the data, 4096 is an important number. So the data cannot capture frequency content above the Nyquist frequency fs over 2, 2048 hertz. 10 to the what is 4096? 10 to the what? I don't know. What is it? Freaking 10 to the what, dude? I don't know. 10 to the something. Alright, whatever. Or no, it's 2 to the something, right? 2 to the... I don't... Who cares? That's okay. How would it be 10 to the something? 10 to the something is always... Alright, I'm stupid, my bad. That's okay because gravitational wave 150914 only has detectable frequency content in the range 20 hertz to 300 hertz. Bro! That's so good. But I don't care. You can see strong spectral lines in the data. They are all of instrumental origin. Some are engineered into the detectors. Mirror suspension resonances at 500 hertz and harmonics, calibration lines, control dither lines, etc. And some 60 hertz and harmonics are unwanted. We'll return to these later. Whatever any of that means, who cares? Okay, so 20 hertz, 300 hertz. You can see strong spectral lines. The data, they're all instrumental origin. Cool. You can't see signal in this plot since it's relatively weak and less than a second long. All right. While this plot averages over 32 seconds of data, so this plot is entirely dominated by instrumental noise. Later on in this tutorial, we'll look at this data sampled in full. 16,384 hertz, 2 to the 14, okay. Whitening. From the amplitude spectral data above, we can see that the data are very strongly colored. Noise fluctuations are much larger at low and high frequencies, and near spectral lines reaching roughly flat white minimum in the band around 80 to 300 hertz. We can whiten the data, dividing the noise amplitude spectrum in the Fourier domain, suppressing the extra noise at low frequencies, and the spectral lines to see the weak signals in the most sensitive band. Okay. Whitening is always one of the first steps in astrophysical data analysis. Searches, parameter estimation. Whitening requires no knowledge of spectral lines. Only the data are needed. The resulting time series is no longer units of strain. Now it's in units of sigma away from the mean. I don't know what this means, though. Whiten the data. Dividing the noise by the noise amplitude spectrum in the Fourier domain. Suppressing the extra noise at low frequencies. Okay. Sure. Sure, dude. Whatever you say. We're writing a function, apparently. So we'll just cut this out. So whiten takes the length of the strain, does some crap with it, and then it returns it. Okay. New plot. Plot the whitened strain along the best fit numerical relativity template. Oh wow, it looks way better. Band past the data. We will also band past the data. Dang, man, this is freaking, some real stuff. So this one's crap. This one's a little bit better. And then this one's the best that we got so far. Where we have whitened the freaking thing. The signal. Cool! This is what they look like. Cool, dude. Matched numerical relativity waveform. So one of the general relativity templates that kind of matches it. Okay. Cool. Alright. Whitened strain. Time. Okay. Whatever. So there you go. That's awesome. That's good. The signal is now clearly visible in the whitened and band pass data. So how does it get band passed? band. Oh, right here. Suppress the high frequencies with band passing. Okay. I don't even know what this is, but it's some math. Okay. Alright. I wonder where we're going with this. The signal is now clearly visible in the whitened and bandpass data. The DC offset between H1 and L1 and data is visible in the first plot and is no longer visible here. The bandpassing cuts off frequency components below around 20 Hz and above around 300 Hz. The signal is visible as an oscillating sweeping from low to high frequencies, from negative 0.1 seconds to 0, and damping down into random noise. The signal looks roughly the same in both detectors. We had to shift the L1 data by 7 milliseconds to get it to line up with the data from H1, because the source is roughly in the direction of the line connecting H1 to L1. And the wave travels at the speed of light, so it hits L1 7 milliseconds earlier. Also, the orientation of L1 with respect to H1 means we have to flip the sign of the signal of L1 to match the signal of H1. It's the exact signal we expect from the spiral merger and ring down of two massive black holes, as evidence matched by the good matched by the numerical relativity waveform in the back. Okay. LIGO uses rather elaborate software suites to match the data against a family of such signal waveform templates to find the best match. Software suites. Okay, cool. This procedure helps LIGO optimally separate signals from instrumental noise and infer parameters of the source, masses, spin, sky location, orbit, orientation, etc. Spectrograms. Woo! Let's do it. Freaking do it, dude. What are we really doing here, though? We make a spectrogram. Like, whatever. Cool, right? Does it matter? Maybe. And we got number 1, 2, 3, 4. Good. 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 Here the spectrograms. Okay. Cool. I don't even know what they mean, but that's fine. Whatever. They're cool. They're chilling. Like, whatever. In the above spectrograms, you can see a lot of excess power below negative 20 Hertz. Where's negative 20 Hertz? Like, where, though? Here's frequency in Hertz. Oh, alright. Well, we don't even get a view of that, but that's fine. Below 20 Hertz. Oh, so like maybe this yellow. As well as strong spectral lines at 500, 1,000, and 1,500. It's 500,000. So the yellow, okay. Also evident that the amplitude spectral density is above. The lines multiple. Alright, cool. Am I still alive? Yes. Okay. Imagine watching this, bro. It's probably the most boring thing ever. Nobody would watch this, right? That would be insane, dude. The lines at multiple 500 HC are harmonics of the violin mode. The fibers holding up the LIGO. The signal is just faintly visible here at time 0 below 500 Hertz. We need to zoom in around the event in time. Frequency range 20 to 400 Hertz and use whitened data generated above. Okay. And then we get this time domain filtering. Now let's filter the signal using in the time domain using bandpass to reveal the frequency and notching spectral lines. Okay. What do we get now? This? Okay, white noise, filtered white noise, filter response. I don't even know what we have anymore. This doesn't even look like gravity wave signal. Gaussian noise, blue is white, flat frequency, cut. Okay. Filter the data and plot it now. What is this now? The same thing? Now, as with whitening signals, oscillating sweeping from low to high frequency, negative 0.1 seconds to 0. Make sound files. Make wave sound files from the filtered. We make sound files. Listening to a black hole. Cool. Cool, dude. Alright. That's cool. Now what? I think it's good. I think it's a good tutorial for sure. Hands-on, son. What is this?
September 14th, this wave reached Earth. And then it's completely equivalent. It's just writing one to the other. And then if you would like to know the power, you just square the electric field. So you take the complex conjugate and you multiply, and you get this expression over here, or this one over here, again, equivalent. So that is what you expect for the output power on that photodetector as function of a phase difference, and the phase difference will be induced then by, for example, a gravitational wave. So with an installation like that, Michelson, about more than 100 years ago, did his measurements on the constancy of the speed of light, and was capable to determine the movement of a fringe by something like
Upload more leak code. Hey, Sanjana, I do have a Patreon with some videos I haven't posted on YouTube if you want to check that out. I mean, I upload every day almost. I mean, you know, I wish I could upload more, but you know, I have a job and stuff. So, but I try. I mean, you know, I have a filmer and an editor, and we go and we make videos every day almost. So, you know, I try as hard as I can. Let's see. But I will be uploading more this week, in the next week.
Okay, so Yo has already introduced you to all of our detectors, and so I won't bother to go in any level of...
Introduction to GWPy. Basics of compact binary searches. Who are these people? It's kind of random. Who gets into this stuff, you know? It's cool though. I think I'm gonna get off and watch these. Seems important to watch. You can download it. Detection papers. Read some papers on it. And then what do you do though? Alright, I'm gonna get off and check this out. So thanks for watching. I know nobody really watched, but it was I'm just like chilling kind of. Put a nice hour in though, just figuring some stuff out, getting everything set up on this guest account on my computer. I'm gonna watch those videos. It's updated and pursue this for sure. So thanks for watching. I will be doing LeetCode. So see you guys soon.